In this video, we're going to learn about lenses. Lenses are a very important application of refraction. When we studied mirrors, the behavior of light that was responsible for the effect that we saw in mirrors, the formation of images, was reflection. In the case of lenses, the behavior of light that will be involved mostly is refraction. After watching this video on lenses, you'll then go and complete some independent work to learn about the application of lenses, including the eye. And so in the eye, you'll notice that we all have lenses, and these lenses are actually a special type called converging lenses because they make light rays meet. And by shape, they're called convex lenses because they bulge outwards. And so I want you to know that in your eye, you have a converging lens that focuses light rays onto a special part in the eye, which sends signals to the brain to allow you to see an image. During this presentation, we're going to learn about the characteristics of various types of lenses, the converging lenses and the diverging lenses. We're going to learn how to make ray diagrams for converging lenses and diverging lenses. And in part 2 of the lens lesson, we're going to learn about the thin lens equation and how to apply that. It's a more numerical way to represent these ray diagrams, more quantitative, I should say. And then, like I said, you're going to do some independent work to study the applications of various types of lenses in society. So lenses are just basically pieces of glass or plastic that are transparent, so they let light go through them, and they bend light in predictable ways. So we can use the fact that they bend light in predictable ways to use them in various types of applications. Some lenses, called converging lenses, will bend light in such a way that they meet at a point called the focal point. Other lenses will bend light in a way that they do not meet. They actually move away from each other, as you can see here, but their traceback rays meet, as you can see over here. So the fact that these light rays move away from each other, the refracted rays move away from each other, means that this is a diverging lens. So we have converging lens that makes light rays meet, and diverging lens, the diverging lens makes the light rays move away from each other. Just like we saw with mirrors, lenses will produce images that we can describe using salt, and salt will apply in the same way that they did in mirrors. They'll have the same meaning. Make sure, though, that when you represent size and location, you use HI and HO, and then for location, use DI and DO. So as mentioned, there are two types of lenses, diverging lenses and converging lenses. Diverging lenses are called that because of what they do to light. They diverge light rays that are parallel to each other and parallel to this thing called the principal axis, similar to what we saw in mirrors. Converging lenses are called converging lenses because they make light rays meet. Light rays that are parallel to each other and to the principal axis will converge onto a single point called the focal point. These lenses can also have names based on their shape. So a diverging lens, another name for that is the concave lens, because it curves inwards. It's thinner in the middle than it is at the edges. And the converging lens can be called a convex lens because it bulges outwards on both sides, so it's thicker in the middle than it is at the edges. Diverging lenses, they can be used in eyeglasses and telescopes, and you'll learn about that when you do your independent research. For diverging lenses, they're always going to produce an image that's virtual, small, upright, and actually closer to the lens. So in a way, diverging lenses are kind of like the diverging mirrors, which were actually convex mirrors. So it's a bit of a flip there in terms of the shape, but in terms of what they do to light, diverging lenses and diverging mirrors, in other words, produce similar types of situations. The converging lenses, they will produce images that are different depending on where the object is. So converging lenses, they converge light just like concave mirrors do. Concave mirrors are converging mirrors, and so essentially, if you remember, wherever the image depended on where the object was placed. So converging lenses are similar to converging mirrors, which were concave mirrors, and diverging lenses are similar to diverging mirrors, which were convex mirrors. So try to make the parallel between those similarities. For converging lenses, we can use them in cameras, projectors, reading glasses, and magnifying glasses. And again, you're going to read up on that when you do your independent research on the application of lenses. So now we're going to take a quick look at the anatomy of a lens. We're going to start off by looking at the convex lens. The convex lens, again, is called convex because it bulges outwards on both sides. In reality, this is called a biconvex lens because it has two convex sides. if you were to chop the lens in half, left and right halves, and you had to draw a line to do that, that line would be called your axis of symmetry. So it's the line that is represented by a dotted line, represents the midway point between within the lens. So the left side and right side can be divided equally by the axis of symmetry. There's also a line that can divide the lens equally top and bottom. That's called the principal axis. It cuts the lens in half from top to bottom. And where the axis of symmetry meets the principal axis at the middle there, that's called the optical center of the lens. The important thing I want you to remember about the axis of symmetry is that this is where the refraction happens, and I'll show you that in just a little bit. Just like mirrors, lenses have focal points, except a lens has two focal points because, well, light goes through both sides. It can enter through this side here, or it could enter through this side here. It all depends on where your object is. So let's say the object was on the left side of this lens over here. Light rays that are parallel to the principal axis and to each other will converge onto the focal point. The focal point that the light rays actually converge onto is called the primary focal point, or sometimes called the principal focal point. The distance from the optical center to the focal point is called the focal length, and again, it has to be from the optical center, not from the edge of the lens, but from the optical center of the focal point. It's called the focal length. If the object was on the other side, well, then light rays would converge onto this secondary focal point represented by f prime. This is an f prime here, and it would be the same distance away as your primary focal point. So if this was, let's say, 6 centimeters, then this is also 6 centimeters. It all depends on where your object is. So in the case of a converging or convex lens, the primary focal point is on the opposite side of the lens of the object, and that'll be important because we'll see for diverging lenses it's a little bit different. And over here we can see the incident ray. That's the ray that goes into the lens, and this is a refracted ray, the ray that comes out of the lens and bent due to the different index of refraction of air compared to the lens itself. Here we just have a formal explanation of the principal or primary focal point versus the secondary focal point. Again, if my object is on, let's say, the left side of the lens, light rays from the object would go through the lens and meet at the focal point on the opposite side of the lens, and the primary focal point would be at the same distance but just on the other side, so equal distance from each other, equal distance from the optical center. So if this was, again, 6 centimeters, well, this side over here would be 6 centimeters as well. Make it a good practice to label both focal points, because when you're doing ray diagrams, you'll have to know where both of them are. The diverging lens has a similar anatomy, except for the fact that it is a concave lens or biconcave lens, because it has two concave sides. It's thinner in the middle than it is at the edges. It also has an axis of symmetry that separates it into equal left and right sides, and it can also be cut in half from top to bottom using the principal axis, and also has the optical center in between, or where the axis of symmetry and principal axis meet. These lenses also have focal points, except the primary focal point this time is actually on the same side of the lens that the object is on, and you can see why through this animation. So when light rays parallel to each other into the principal axis enter the lens, they're not going to converge, rather they're going to diverge. So they actually won't meet at a point on the opposite side of the lens. They won't meet at a point on this side here. But if you do the traceback rays, you'll notice that their traceback rays will actually appear to meet at a point on the same side of the lens as the object, and that will be our focal point in that case. So this is our primary or principal focal point. If the distance from the optical center is 6 centimeters, well, then the distance from the optical center to the secondary focal point would also be 6 centimeters on the other side, because they'd be the same distance from that optical center. So again, this time the primary focal point is on the same side of the object, whereas in the converging lens it was on the opposite side of the object. This is just a formal definition of the principal focal point and the secondary focal point as it relates to the diverging lens. Again, if the object is on the left side of the lens in this case, the primary focal point would be on the same side, because it's where the traceback rays appear to converge, even though the actual rays are diverging from each other. If the object was on the other side, however, you would see the same thing, just reverse, and so the primary focal point would be over here instead. But right now, as it stands, the object is on the left side, so the primary focal point is on the left side, and the secondary focal point is on the right side. When dealing with lenses, it's important to understand that refraction actually happens 2 times. As we can see here, light rays from the air enter the lens and refract. Upon entering the lens, they refract, so this is the first time, and upon leaving the lens, they refract again because there's another change in speed. So the first change in speed was from air to plastic or glass or whatever the lens was made up of, and the second was from glass to air or plastic to air, or again, whatever the lens was made up of. However, since we are dealing with thin lenses, which are very, very thin, we're only going to see refraction happen once, and that refraction is going to happen at the axis of symmetry. So when we are drawing ray diagrams, we're going to show the incident ray hit the axis of symmetry, and then the refraction should happen at the axis of symmetry. So here's a little bit off as well. It shouldn't happen at the edges. It should happen at the axis of symmetry. And that's only because we're dealing with thin lenses. We can assume that the refraction is only going to happen once per set of rays, of course. So we're going to start off by studying the converging lens cases. Just like we saw with converging mirrors, in other words, concave mirrors, the image depends on where the object is located. It could be at F, 2F, between F and the optical center, between 2F and F, beyond 2F, and that will give us different images. So we're going to see which convenient rays we can draw in order to predict where the images will be, and there are 3 that I will teach you. Here we have the steps for drawing a ray diagram when an object is in front of a converging lens. If not already drawn for you, you should add in your axis of symmetry because that's where all the refraction will happen. Make sure it separates the lens into equal left and right sides. And if your principal axis is not drawn for you, do the same thing. Make sure it separates the lens into equal top and bottom halves, and then your optical center would be in the center there. And if you're told your focal point but not given it, you need to measure it from the optical center. So if the focal length is 10 centimeters, you need to measure 10 centimeters from the optical center to find your focal point on both sides. And then depending on where the object will be, you'll have a primary focal point and secondary focal point. So if your object is on this side over here for a converging lens, then your primary focal point is on this side, and your secondary focal point is on the same side of the lens as the object. So in this case, we're going to draw in our principal axis, and that separates the lens into 2 equal halves, upper and lower half. You're going to place your object on the principal axis, so the base of the object goes on the principal axis. In this case, we're going to do the scenario where the object is located at 2 focal lengths away from the lens. So what I do for practice is I like to also label 2 focal lengths on the other side where it's not labeled at the moment. So for example, I might have 2 focal lengths over here. If 2 focal length is 10 centimeters on one side of the lens, it's also 10 centimeters on the other side from the optical center, of course, not from the edges. I might be a little bit off only because I didn't use a ruler. So the first ray that you're going to draw is one that goes parallel to the principal axis. That's our first incident ray. Notice I drew an arrow, and it stops at the axis of symmetry. Once it hits the axis of symmetry, it's going to refract so that it goes through the focal point on the other side, through the primary focal point. Make sure you draw another arrow to show your refracted ray is different from your incident ray. Now, the second ray that I draw is one that goes through the optical center. When a ray goes through the optical center, it does so little refraction that it's negligible. So we can essentially draw it going straight through. Now, I still like to show 2 arrows, one before it hits the optical center and one after it hits the optical center. That tends to be the one that students usually forget. So please make sure that you do not forget it. I put a note for it over here. And technically speaking, we already did find our image. It's where these real refracted rays meet. But this is not the only; these are not the only two rays that we can use. We can have a third ray, a third special convenient ray, to allow us to make sure that our work actually is accurate. So the third ray is, as you saw here, a ray that goes from the top of the object through the secondary focal point, hits the axis of symmetry. Once it hits the axis of symmetry, it's going to refract such that it's parallel to the principal axis. And you'll notice that it meets where the other two special rays met. And this over here would be the top of the image, because the rays came from the top of the object, and the base would remain on the principal axis where it is. So here we have our image, and you'll actually notice if you measured the distance, the image is actually located at 2f. This is very similar to the situation that we had with the concave mirror or the converging mirror, located at 2f, the center of curvature. You had an image that was the same size, that was the same distance away from the lens as well, that was real, and that was basically inverted at the same location. Except in the case of a concave mirror, they're on the same side of the mirror, whereas in the case of a converging lens, they're on opposite sides of the lens. So you could describe this using SALT. HI is equal to HO, A is inverted, DI is equal to DO, and then its type is a real image. Because this is a real image, this could actually be projected onto a screen since it's made by real rays. So you should be able to attempt this for a variety of other scenarios, such as that for the object being located beyond 2f, for the object being located between 2f and f, for the object located at 2f, which we already did together, for the object being located at the actual focal point itself, and for the object being located between the focal point and the optical center of the lens. And for some of those cases, you may have to draw traceback rays, because it is possible to get a virtual image for lenses as well, just like we saw for mirrors. The answers will be provided to you on the next set of slides. I'm going to quickly sketch these just to show you what I expect of you with these scenarios, but you should be able to do them yourself using the special rays that we saw. So for example, if I have an object beyond 2 focal lengths, I'm going to do my ray that's parallel to the principal axis. It hits the axis of symmetry, and once it hits the axis of symmetry, it's going to refract such that it goes through the focal point on the other side of the lens, and don't forget to put your arrow there. You can do another ray that goes through the focal point on the same side of the lens that the object is on. It hits the axis of symmetry. Once it hits the axis of symmetry, it refracts such that it is parallel to the principal axis. Mine's a little off right now because I'm not using a ruler, but you will be using a ruler. And then my double check ray I usually do is one that goes straight through the optical center. It barely refracts, so we don't have to indicate refraction. And you need to make sure that you put an arrow for the ray that went through and for the ray before it actually hit the optical center. And this is the point where they both meet, or where they all meet, and you'll notice that your image is inverted. It's real, it's smaller, and it's also closer to the lens than the object was. So you should become familiar with that case, so that when I give you something like this in a quiz or a test, you know where it should roughly end up, between f and 2f, and you won't be thrown off. You shouldn't be guessing. You should just be kind of confirming what you already know when you're doing these diagrams. Here we have the case when the object is at 2f. We already did the situation together, so make sure you retry it and you can actually perform this. In this case over here, we have an object located between 2f and f, and so just to show you with a ray diagram, a quick sketch, you do one light ray that's parallel to the principal axis. It hits the axis of symmetry and refracts there. It's going to go through the focal point on the other side, so right over here. You're then going to do one ray that goes from the top of the object through the focal point, hits the axis of symmetry, and refracts such that it's parallel to the principal axis. And where they meet is where the top of the image should be. We'll do our double check ray though, right through the optical center, and it meets up with the other ones over here. Make sure you have one arrow before and one arrow after the rays of the optical center. And so in this case, we can see that the image is inverted, the image is real, the image is larger than the object, and the image is farther away from the lens. In fact, this is what we use in movie projectors. We're able to create a larger image that can be projected on the screen because of the real rays here, and it's a larger image. The purpose of the projector is to take a small image and make it larger for everyone to see. However, you'll notice that our image is inverted. So think about how you have to place your object in order to get a movie that people don't have to watch upside down. Here we have the case where the object is located at the focal point, and just like we saw with converging mirrors or concave mirrors, there will not be an image formed here. So we can do our ray parallel to the principal axis. It goes through the focal point on the other side. It's a bit difficult to do the ray that is going through the focal point on the same side of the object because you're on it, but what you can do is you can do the one through the optical center, which does not refract. You'll notice the rays are actually parallel to each other. You could do traceback rays if you want to, but since the rays are parallel to each other, the traceback rays will also be parallel to each other, and as a result they'll never meet, so they do not cross. So you will not have an image formed at this location here. And make sure again for the ray that goes to the optical center, you have an arrow going, you have an arrow before and an arrow after the optical center as well. And finally, we get to the case where the object is located in between the focal point and the axis of symmetry. So to do this, you're going to have traceback rays. My first ray is the one that goes parallel to the principal axis, hits the axis of symmetry, and reflects so that it goes through the focal point on the other side. You can make a traceback ray for this. And again, I will be off because I'm not using a ruler, but you will be. You can do one that goes through the optical center because it's a bit difficult to do the one that goes through the focal length. You could do that as well, but we're going to do the one that goes through the optical center like this. You'll notice the rays are actually diverging on this side, but that means that their tracebacks are going to meet. And they will meet right up here, assuming you're using a ruler. And so we get an image that's upright, that's larger than the object, that's farther away from the lens, but it's virtual since it's made by these traceback rays. So I know I said that the ray that goes through the optical center does not refract, and so some of you might be thinking, well, why does it have a traceback ray? There actually is a little bit of refraction still it's negligible, we don't really see it, but because there's a little bit of refraction happening, there's still a traceback ray that can form from that. So even though this makes a larger image, this cannot be used for projectors. I need you to think about why this location can't be used for projectors. I told you guys the object has to be located between 2F and F for the projector. Putting the object between F and the optical center will give you a larger image, which is what you want, but there's something still lacking that will allow it to be actually useful for the projector use. This location is usually used for magnifying glasses, so when you're trying to, let's say, read some small letters in a newspaper or in your notes, you might use a magnifying glass to make them look magnified or enlarged. And so when you do that, you'll actually notice that the letters are still located on the same side of the lens that the book is on or that your page that you're reading is on. It's not on the opposite side of the lens. So this is a scenario where your image is on the same side of the lens that the object is on, and it happens to be a virtual image. Here we can see the example of the magnifying glass making the image larger. The observer is on, the side that you're on, looking through the magnifying glass. The image is on the opposite side of the magnifying glass along with the object. Over here we can see a convex lens or converging lens converging these light rays onto the primary focal point on the other side. Here we have a summary of the different cases that we saw for the objects going through, for the objects located at different positions relative to the focal points of the converging lenses. You should know all of these scenarios and know when they're used. Over here we can see how the image is used and when the image is used in practical application purposes, and you should be able to explain why that's the case. Now we're going to go and take a look at ray diagrams for diverging lenses. So if you are not given the axis of symmetry, you need to make sure you draw that in so it separates the lens into equal left and right halves. You're going to use a ruler to make sure you're as precise as possible, and then you're going to do the same thing for the principal axis so that you can find the optical center and then measure where the focal points would be based on the focal lengths provided. Most times they will be provided to you and they'll already be drawn in, but if they're not, you need to draw them in yourself. So the fun thing about diverging lenses is that they're really always going to produce the same type of image. They're very similar to diverging or to convex mirrors. They'll always produce the same type of image regardless of where the object is located. So if we pay attention to these diagrams here, regardless of where the object is located, the image is always going to be virtual, formed by traceback rays, as you can see over here. It's always going to be upright, as you can see in these situations here. It's going to be smaller, so reduced in size, the HI smaller than the HO, and it's going to be closer to the lens, so DI is smaller than DO. So I know over here it looks like we have traceback rays forming an image with some real rays. But in reality, keep in mind that this ray that goes through the optical center did refract a little bit, so there's actually a traceback ray underneath the incident ray that you see here. So the image is actually forming because of this traceback ray here and a traceback ray underneath that incident ray that we can't see because they're so close to each other. So that is a virtual image. It's not part virtual, part real. It's strictly a virtual image, and that's why you could not project this onto a screen. So we're going to start off by drawing our principal axis to cut the lens in half. We are going to place the base of the object on the principal axis. We're going to draw our first incident ray. It's one that's parallel to the principal axis. Now keep in mind that these rays are, these lenses are going to be diverging lenses, so they will not focus light on this side. Instead, they're going to diverge the light ray. So the light ray is going to move. The light ray is going to move outwards. Now, the point here is that, first of all, refraction has to happen at the axis of symmetry. So the incident ray should stop at the axis of symmetry, and the refracted ray should begin there as well. You're going to draw the refracted ray such that it looks like it's coming out of the focal point directly behind it. And in fact, that's what needs to happen because that's where you need to draw your traceback ray. So you need to draw your traceback ray for that refracted ray so that it goes through the focal point that's on the same side of the lens that the object is on. The next ray that we'll do is one that goes through the optical center, and again that doesn't refract very much, so we don't have to show that refraction. In reality, keep in mind that there is a traceback ray just along this first incident ray. We just don't see it because it's directly behind it. So here is where the image would form. There's a third ray though that we can use in order to make sure that we are on the right track for that. That third ray is one that goes towards the focal point on the other side. So it's about to get to the focal point here, but it stops because there's a lens in the way. Once it hits the axis of symmetry, it's going to refract parallel to the principal axis, and then you draw the traceback of that refracted ray. And you'll notice it meets where the other rays have met. So that area where they all met is where the image will form. Because it's formed by traceback rays, it's a virtual image. You'll notice that it's upright. You'll also notice that it's smaller than the object. So this is our object here. This is our image. And it's actually closer to the lens than the object was. Because it's virtual, this cannot be projected onto a screen. You should be able to do this scenario for a variety of different locations. You'll always get roughly the same results. Even though you get the same results, I do want you to notice some trends. So here we have a variety of objects in red located at different distances from this diverging lens. You'll notice that as the objects approach the lens, so does their image. So the closer the object is to the lens, the closer the image is to the lens. the closer the object is to the lens, the closer the image is to the lens. And the closer the object is to the lens, you'll also notice that it produces an image that's larger. The farther away that image is from the lens, the smaller the image is going to be. But it's always much closer to the lens than the object was itself. So whenever you're doing these ray diagrams for lenses or even mirrors, you need to identify as many trends as possible. It's just so that when you're doing a test or quiz, you're confirming what you have a general sense of already, as opposed to just guessing and hoping that you're doing it right. Here we can see an example of a diverging lens. It's making the image of the object look smaller compared to the actual object itself, and it's formed on the same side of the lens that the object is on. Here we can see that concave or diverging lens diverge these light rays away from each other. We know that they're moving away from each other, but their tracebacks appear to meet behind the lens, as you can see there at the primary focal point. Here's a summary of the different lenses that we saw, the diverging lenses and the converging lenses. Make sure that you can make the parallel between a diverging lens and a diverging mirror, right? The diverging mirror is the one that's convex. It might have a different shape, but it does very similar things because it diverges light as well. The converging lens is similar to the converging mirror. It might have a different shape. It's concave as opposed to convex like the converging lens, but it converges light, so it has a similar pattern of image formation that you would see in the converging lens. So make that parallel and understand how they're related to each other in that sense. In order to see an image formed by a lens, your eye has to be in the way of the refracted rays. So over here we have a magnifying glass. We have a small object, and you'll notice that the light rays are bending. Refracted rays go into our eye, but because we don't realize refraction is happening, our brain fills in the blank with these traceback rays, and we see that larger upright image that's behind the lens and is also virtual. We could not project this onto a screen where the object is located at the moment because it is formed by these traceback rays. But if you move this, let's say somewhere over here, then you might get a real image that you could project onto a screen. The same can be said regarding the images formed by these concave lenses or diverging lenses. Your eyes have to be in the way of the refracted rays, but again, because we don't take into consideration the refraction, our brain does not realize it's happening. We fill in the blanks with these traceback rays over here, and we see the smaller image on this side over here, the same side of the lens that the object was on, except it's smaller. It is upright and it's virtual, so we could not use this in the projector. We could not take this and put the image onto a screen. For homework, you should read chapters 13.1 and 13.3, which really covers what we did in the PowerPoint. You should be able to do all the problems on page 553 and 561. There will be some practice worksheets provided to you, as well as some application worksheets for the applications of lenses. You should be able to tell me which applications have which lens and also where the object should be placed in order for the application to work appropriately. There will be a worksheet on the eye for you to complete, along with some simulations to help enhance your understanding of the concepts that we saw in this presentation.